I wonder if I would. Because then you something then you like that. You probably lateral side. Here's when the shaft's going this way. So this way. Now we take it from the top, it's going this way. The offset like this, and it's a negative. So if the shaft is staying still, if you did this top. Don't have this, and it's sharing. This. What's your saying? So, yeah. No. I'm saying, you know how constructed started the problem. It's at the bottom of the shaft, the top of the bottom. The inlights there.
Oh, right.
Through it. It's a box, and a box gets restricted like this. That's a positive slope. So then if we took it from the top and all of the shaft, right?
What's that? Mind if I sit here?
No, please do. And you shift it, now it's or you shifted to go like this.
I'm doing all right.
Yeah.
I swear we cost a lot, but I keep forgetting the routines.
That's a good thing too, Jason.
We're just looking at like four planes.
Yes,
I
I have her again this semester.
You would just multiply that by 6.5 to get the full diameter. Yeah, I know what you're saying. Yeah. Because you that's the negative. I know what you mean. That doesn't make sense. I mean, yeah.
So wait, listen for one of my mechanical engineering. I want it. I'm place number 2. Not really open.
There's seats.
I know, and then I figured I got it.
What?
It's
a cool box.
It's
Like, I mean, obviously I want that 2 days, so like, I'm pretty excited about it.
I know.
All right, it's 4 o'clock. Let's go get started. Good afternoon, everyone. Welcome to day 2 of optimization. How's everyone doing today?
Great. How about you?
Good. I'm doing good. Thank you. Yeah, it's been a hectic first week, but almost at the end, almost at the long weekend. Great. We came back from big summer break, and then we get a long weekend right away. Okay, so today, is this, I guess this is kind of the real first lecture. Last week we kind of just, we're mostly just kind of hanging out, talking about the syllabus. So today is going to be the first kind of real day of notes. We're going to go over kind of, a little bit of reiterating what we talked about on Tuesday, just kind of introducing optimization, but we're going to be a little bit more formal with it today. We're going to see some math, we're going to see some equations. So, today's kind of the real kind of first day. Okay. Other announcements. So your first, so first of all, homework 0, the email homework assignment. Remember that is due on Sunday. I've already had a lot of people email me in the class, so that is good. But if you haven't had a chance to send me an email, just make sure you do that before Sunday, just so I can give you credit for it. Homework 1, which is the first problem set. I am working on it right now. I should have it ready for you guys tomorrow. And the due date, you guys have about a week to work on homework 1. Maybe a little bit. I think I'll have it due the Monday, not Labor Day Monday, but Monday, September 9th. Okay. All right, I think that's it. Any questions I can answer before we get started? Okay. All right, so today's going to be just another kind of introduction today. So this is introduction to optimization. Okay. So on Tuesday, we introduced this idea of optimization. That optimization, at the end of the day, is aiming to get the best result possible given a certain system with certain parameters. Okay? So we're literally optimizing the performance, we're optimizing the results of our system. And the way that it does this is by finding the best values of the system parameters that is active. So kind of the assumption when you're working with an optimization problem, when you're getting to the step of optimization, the system parameters have already kind of been defined. So you're not adding any new variables or anything like that. So you've already kind of have a design kind of already in mind, and you just want to optimize the design to get the most possible performance out of it. Okay. So just a very quick example. Just a visual example. Let's consider the case, let's say that we're designing a building and we want to design kind of the size of a structural column. Say that, we have some building that we're constructing, maybe we're on the second floor or something like that, right? And there's one part of the structure where we have this column, right, that's supporting the building. Fair warning, and those of you who've tried me before, art is not my forte. So sometimes if I draw pictures, you might have to use your imagination a little bit, listen to what I'm saying. I know because that looks like a T, but imagine there's a building up here. Right? And this column is supporting the building on top. Okay, so let's consider just a very, very simple kind of a design problem here where we need to determine the width or the thickness of this column. Thickness is defined by that distance, from one end of the column to the next. Just for simplicity's sake, we'll say that this is a cylindrical column, so the thickness will be defined as the diameter of that column. Okay. We'll call that capital D. So this is a very simple situation. So the value of D could either go up or down, right? So in our design process, we've already determined that there's going to be a column here at this location in the building. All we need to do now is just determine the best value for D. Okay? So let's assume that we're starting with kind of a default value for D, like a base value, and let's consider the possibility of increasing the diameter and decreasing the diameter. Okay, so what do we expect to happen, or what kind of effect on our design do we expect to happen if we were to increase the diameter of this column? Right? So increasing the thickness of a column generally makes it more structurally strong. Okay, so that is a positive. Maybe that's something that we need because we're anticipating some loads. Maybe this is like a two-story building where people are on top, and it needs to be able to support that without buckling or breaking. Okay, that's generally what we like to see in our buildings for them not to fall apart when people get on top of them. But on the downside, of course, if you increase the diameter of the column, that's going to add material. It's going to cost. It's going to require more concrete or more material to make it. So that's increased material cost. There's no free concrete in the world, so someone's got to pay for that. And generally, if you're working on engineering projects, increased cost is usually not a good combination of words to say to your manager. So, that's something you have to consider. Another thing as well, so if this column were on kind of an upper level, right? So say this is a big high-rise building or so, and this column is somewhere kind of near the top. Increasing the amount of material is also going to increase the weight as well. So those are some of the effects that we kind of expect to happen if we were to increase the diameter of that column. Now let's look and see, what effects that we expect to happen if we decrease the diameter. We can just go kind of, point by point here. So, of course, in a simple system like this, going the opposite direction, we expect opposite to happen what's on the other side, right? So if we decrease the value of D, generally we expect to have less strength. But if we decrease the diameter, we also decrease the amount of material that's required, so that means less cost, and also less weight. So both of those generally are positive. Maybe another factor that we haven't considered is that for the interior design, having a thinner column makes it a little bit easier to decorate and for people to move around. Maybe that's better for fire safety as well. Okay, so hopefully this example kind of shows you that whenever when you're kind of at this stage of engineering design, there are always trade-offs in the decisions that you have to make. You can't just, it's not as simple as saying just make the column as thick as possible or make the column as thin as possible, right? Generally, what we expect is that there's some kind of value in the middle of these extremes where the optimal column diameter exists. So the value of that diameter that you're ultimately going to go with your design is somewhere in between those two extremes. Okay. So this, this is a single variable case. Maybe this is a little bit trivial for optimization, but you can use an optimization algorithm in this case to find out what that optimal value is. Okay. And the beauty of optimization is that it can take all of these factors into account, right? And so you can design your optimization problem in a way where it accounts for the strength, it accounts for the material costs, and it accounts for the weight. And optimization is especially valuable in cases where this kind of this thought example that we just did was a single variable case, pretty straightforward. But you're almost never going to have a single variable in your engineering designs, right? So let's say that instead of just the diameter, you're also considering the height of the column, and you're also considering the material of the column. Okay. So in these kind of situations where you have more than one lever to pull. It can be really complicated to find the most optimal values, when you have a lot of different considerations to make as well. So a lot of the problems that we're going to do in this class are going to be multiple design variable problems, because that's kind of where optimization really shines. Is you take a complex system with multiple variables and you find optimal values for them all at the same time. And some common themes that you'll see kind of throughout the class. Cost is almost always going to be consideration when you're doing this project. So in some way, cost is going to be a factor. Sometimes strength is a factor. A lot of times weight is a factor. Sometimes you have other constraints as well. So that's kind of the space that we're going to be exploring in this class. Is optimization. If you kind of look at the entire design cycle, optimization usually comes in fairly late. It's usually one of the last things that you do kind of before manufacturing or fabrication. But it's an important step because it really takes your design and makes sure you get the best performance possible. Okay. Any questions on this so far? Okay. All right. So let's be a little bit more formal. So let's look and see what an optimization problem actually looks like. Okay? So let's do the form. This is the formal definition of an optimization problem. Because like I mentioned on Tuesday that, optimization, of course, in this class, we're going to be using it in an engineering context, but optimization really has its roots in applied math, right? And so, a lot of the definitions and a lot of the, the terms are going to be from math. Okay? I had a more I had a more elegant way to kind of put that in my head, but optimizations are math problems, but so are the majority of engineering problems. So that doesn't really tell you much. But I think let's just jump to the formal definition and you'll kind of see what I mean. Okay. Okay. So the formal definition for an optimization problem is to find. And this is a very, very general definition, so it's meant to kind of encompass a lot. So it's going to seem really dry at first. But we're going to kind of go over every component of this. Okay. So we're going to find the values of the design variables. Notice I have a plural there, design variables, right? So there can be more than one. And technically speaking, you can optimize over endless amount of design variables as well. Okay. So the symbols that we're going to give the design variables is x, and we're going to give it a subscript I. You guys have seen index notation before, I'm assuming in your previous classes. So that's just meant to state that there can be multiple design variables. So that I there is like a numbering, right? And so for instance, there could be x1, x2, x3, so on. Okay. So that subscript I is just the index of the variable. We leave it as kind of a generic I just because this is general for any amount of design. Okay, so we want to find the values of the design variables xi that minimize an objective function f. And this objective function f is a function of the design variable, so that we say that it's f of x sub I. And oftentimes we need to perform what's called constrained optimization. So we want to minimize our objective functions subject to some constraints. And oftentimes our constraints take two forms. Give me a function g, that's I, and another function L. So kind of the that's kind of the statement. So let's kind of see it in more of its kind of mathematical things. We want to find xi where xi is usually some vector quantity. 1, x2, x3, okay, all the way up to xn. Where lowercase n there, that's the number of design variables in our particular system. We want to find xi, which minimizes our function f of xi. Subject to our constraints. So we have our function g, I. We say that is less than or equal to 0. No, xi to 0. For this function g here, we often call these the inequality constraints. And function L here, we call this the equality constraints. I guess I haven't defined it yet here, but this f is an important part. This f is often called our objective function. I know, very, very dry, but we're gonna kind of we're gonna spend the rest of the day kind of picking this apart and kind of defining what these are and kind of giving examples of what these would look like and kind of. But this is kind of the most general kind of catch-all definition of an optimization problem. All right, any questions on this? Okay. So I just gave you kind of the full definition here with a bunch of terms that probably mean nothing right now. So let's kind of go through each part. So the parts that I want to focus on here, that we're going to give more kind of careful definitions to are the design variables. We're going to define that first. Next, we have the constraints. So we're going to talk about those. And then also the objective function as well. So that's 4 definitions that we need to go over. So let's start with the design variables. This is probably the most intuitive part of that definition, because we've already kind of seen from the example earlier. Okay. So the design variables are the set of parameters that can be modified during the design process that can modify the performance of the system. So your design variables are the parameters that you are looking to optimize. So thinking back to the example that we did earlier with the column, right? That was a single variable system with one design variable. That design variable was the diameter. Basically, any variable or any parameter in your engineering system that you have some degree of freedom to change, that can be considered a design variable. Let's do another kind of visual example just so you can kind of see. We're not going to formulate this into an optimization problem. I just kind of want to illustrate it to you. Let's look at a gear pair. Started out great and then ended up not so great. It looks like a bacteria or something. All right, I got to draw another one. That's a gear pair. All right. That's enough. That's fine. Two gears next to each other, right? So let's say that this gear pair, even though it looks simple, there's a lot of parameters that actually govern its behavior, its performance, right? So we call this one gear one, call this one gear two, right? One parameter is just simply the number of teeth on the gears, okay? So T1 could be the number of teeth on gear one. And T2 the number of teeth on gear two. We have the width or the depth into the page. We call that depth B. We have the distance between the two gear centers. We'll call that lowercase d. And then we may also have some parameters like maybe the pressure angle of the teeth. We'll call that psi. And then let's say that the material is also so all six of those quantities, T1, T2, B, D, psi, and the material. And the material, technically, there's more than one parameter there. All of these things count as design variables because if you modify the number of teeth on one of the gears, that's going to affect the mechanical advantage. That's going to affect the performance of this system. Because if you change the values of any of these, your gear pair is going to behave differently. So basically, any parameter that has some kind of numerical value in your engineering system that you can tweak, that's going to affect the performance, that counts as a design variable. Okay? Now, whether or not you actually include it in the optimization is another story, right? Because even if you think of any kind of engineering system, if you think of let's say you think of a car, let's even just go simple. Let's look at the car's wheel, right? Or the tires. So the tire probably has at least a couple dozen or so maybe 15 to 20 different variables that affect its performance to some degree, right? Technically you can do an optimization with 15 to 20 variables, but it's usually not prudent to do so. Okay. So oftentimes, when you're looking at a system and you're kind of doing accounting for the design variables, oftentimes you want to do a little bit of kind of filtering yourself and think about kind of what are the design variables that I'm actually most unsure about, because there are some design variables that you kind of really don't have any control over. So usually right off the gate, there are some design variables that already kind of have a fixed value, right? And this could be for a variety of reasons. So, maybe you're stuck to a certain kind of, certain values of the number of gears or number of teeth on the gears, right? Or maybe you're stuck with a certain width just because that's all the manufacturer has in your stock, right? Maybe you're fixed to a certain material, you can't really change that. So, oftentimes, some design variables will already have a fixed value, and you don't have to optimize over everything, because it's usually not practical to optimize. So what I've always learned is that, when you're tackling optimization problems is to think about the design variables that can benefit the most from optimization. There's a thing in optimization called the curse of dimensionality, where kind of the more design variables that you add to the problem, the more expensive and the more kind of time consuming that it's going to be. Yeah. Because technically, yeah, the algorithms that we're going to cover in this class, you could technically use it to optimize 50 design variables at the same time. Whether or not you're going to live long enough to see the end of that algorithm is a different story, but technically you can. But typically you want to try to limit the amount of design variables that you're optimizing. Because each one that you add kind of increases the cost of the upgrade on an exponential scale. All right, any questions on this so far? Okay, so those are the design variables. So I think those are kind of the most straightforward thing to understand. Let's talk about constraints. So when you're doing engineering design, right, and you're determining the values of your design parameters for design variables, there are certain limitations in terms of the what I call kind of permissible values for the design. But just a very quick example is that, usually, we work with positive numbers in engineering, right? It doesn't make sense to have a negative length or a negative value of the resistance, right? This is something that, we don't really think about just because, without optimization, people are kind of choosing the values of these kind of intuitively. And so intuitively, you're never going to select like a negative length or negative resistance or negative capacitance. But the thing with these algorithms is that, they were kind of designed by mathematicians to be kind of general. And sometimes, sometimes there are certain algorithms that will push negative. And so design constraints they kind of act as a way for us to enforce what a permissible value is, and to do so kind of mathematically within the algorithm. So these are really important because some of the algorithms that we're going to go over in this class, especially near the end of the class, they're very much kind of a, set it up and let it go kind of thing, right? So you start the algorithm, but once it starts, you kind of have very little control over kind of where it's going to go and what values it's going to find. And so design constraints are a very important part to make sure that, whatever result that you get, whatever optimal result that you get, is going to be, permissible. Okay. So I'll give you kind of an example about why kind of this is important. So let's say that, we were designing our column from Fullerton, right? And let's say that your boss says that it's extremely important to minimize the cost as much as possible. And so let's say cost is the only consideration. Cost is like, I don't care about anything else except for cost. Okay. We can come up with a formula that kind of specifies the cost of building a column. And so if we assume that the cost is proportional to the volume of the building, and so we just basically take directly the material costs. And so we take the volume of a cylinder. The volume of a cylinder is pi 4 times the diameter squared times the height. Right here is the volume. That's just simply the volume of our cylinder. And then the cost is just going to be some factor or some coefficient multiplied this, which is the cost of the material, right? Usually for material, you pay per cubic inch or per cubic foot, something like that. We'll call this A. A here is the cost. So if your boss is saying that, cost is the only factor that's going to be important in this design, this is what your function is. This is what what you want to optimize. Okay. And let's say that, we'll keep it simple. We'll say that the height of the column is fixed. The only variable that we can optimize here is the diameter of the column. Okay. So without knowing anything about the building, without knowing anything, right? What is the value of D that minimizes this cost? Zero, right? So if we have no column, we have no cost, right? Easy problem, right? But of course, that can't happen, right? That column was put there in the design for a purpose. If you don't have a column there, the building is going to fall apart. And so one thing that we can do to kind of alleviate this is put a constraint on the value of D. Let's say that D, I'm just gonna make up numbers at this point. D has to be greater than or equal to, let's say, 30 inches. And that's a constraint that we have to work with. Let's say that we performed a structural analysis, we performed, finite element analysis. And what we found is that if the diameter is less than 30 inches, then it's not going to be able to support the structure with any kind of degree of or factor of safety. Okay. So that's one example, right? And so that's one example of a constraint that's really needed in an optimization like this to make sure that our design actually works as intended. Otherwise, you could get kind of nonsensical answers like. Okay. Any questions on this so far? Okay. So this type of constraint that we have right here, this is an inequality constraint. So inequality constraints kind of specifies a region or specifies a range in which certain values take place usually. Inequality constraints can be used other ways, but that's kind of the most common application is that there's a certain range or a certain certain region where our design variables have to take their values that are permissible, and inequality constraints are a way to kind of enforce those things. Okay, and so if you recall back from our formal definition of an optimization problem, we had one constraint that was d less than or equal to. So that expression there with the inequality constraint. So the reason in the formal definition we have less than or equal to 0, that may seem kind of strange just because we may not know exactly what the range is. In fact, that the example that I have boxed up there is greater than 30, right? When you have 0 on one side of the equation, that's what's generally known as the standard form of the constraint. And most, I would say all constraints you can actually work on algebraically to put it in standard form. Okay. So if we take that example up there earlier, right? I'm sorry, the less than or equal to sign is also kind of standard form. So if we want to take that example up there and put it in standard form, right? We have d must be greater than or equal to 30 inches. Okay. In this form, d is greater than or equal to 30 inches. Even though my opinion is that this is kind of the easiest way to view this. This is not technically standard form. Okay. So standard form would be to subtract d from both sides. Right. Remember, an inequality equation is still an equation, so you can perform kind of basic algebra on it. And so if you do that, we have 0 on one side is greater than or equal to 30 minus d. And of course, we can kind of flip this around, kind of put things on both sides. Kind of swap their places. Let's say 30 minus d less than or equal to. So even though it looks really weird, but this right here is the standard form of the constraint.
It's not like for the sake of coding.
It's for the sake of mathematical consistency. So when you talk about constraints and you compare it to other optimization problems, it's always kind of in this. Yeah. Programming wise, you can probably do either. In fact, it might, just because of modern programming too, you can do less than or equal to in like MATLAB, probably the formal ways that you can do. But technically, this one down here is the standard form.
Questions for me? Multiple numbers instead of just like.
Yeah. No, great question. So if you oftentimes you want to specify like a minimum and a max, but you actually need to set those as separate constraints. So let's say we have an upper bound too, right? So let's say that d has to be greater than or equal to 30 inches. But let's say we have another constraint that d has to be less than or equal to 50 inches. So that's how you specify an upper bound. You just have a second. And of course, we can put this in standard form as well. We can say that d minus 50 is less than or equal to. Any other questions on this? Okay, next let's look at equality constraints. So equality constraints are, you're never going to see them in a one-dimensional problem just because it turns your problem trivial. Equality constraints are something that you see in two-dimensional, three-dimensional, multi-dimensional optimization problems. And what their main role is, equality constraints are mostly used to specify relationships between different design variables. Because oftentimes, when you're doing kind of an engineering design, the value of one variable is going to affect the value of another variable as well. And usually there's some kind of relationship in it. So one example. Yeah. So I'm just going to do just a straight up math example in this case. So let's say we have a two variable optimization, x1, x2. So let's say there's such a relationship where, as the value of x1 changes, that's going to affect x2, right? So let's say that we can express this as an equality constraint as 3x1 plus 4, 2 has to equal 24. So no matter what values that we end up choosing for our optimization, this equation here has to be satisfied. Okay? So let's say that we run this through an optimization algorithm, and let's say that we find that the value of x1 is 3. And so if the optimal value for x1 is 3, and this equality constraint has to be satisfied, that tells us automatically what the value for x2 is, right? And so to kind of solve for this equation, we have 3 times 3 plus 4, 2. Okay. So what I'm doing here is I'm using this constraint to find the value for x2 given the value for x1. So if we already know that the optimal value for x1 is 3, I'm just plugging 3 into that equation for x1. 3 times 3 on the left is 9, and so I'm going to subtract 9 from both sides. So subtracting 9, we have 4x2 on the left, and on the right we have 24 minus 9 is 15. Okay. You'll pick a more convenient number. That's okay. Okay, so if we divide both sides by 4, we get x2 is equal to 15 over 4. Yeah. So in this case, I just made up an optimal answer for yeah. In truth, you would need an objective function to determine which we're going to go next. Okay. So before I move on to the objective function, I do want to kind of show one thing. Okay. So you're going to see these plots and lots. In fact, you're going to see these plots in homework 1 as well. And so this is a concept of a design space. And this is particularly relevant with constraints because we can basically visualize our constraints using this concept of a design space. So a design space is essentially a visualization of the of the values of the design parameters. Say a visualization of the possible values of the design. Remember, we haven't got to optimizing yet because we haven't got to the objective function. But even before you get to the objective function, even before you start optimizing, it's always good to visualize kind of your design space and what the permissible values are. Okay? So just based on our concept of perceiving a three-dimensional world, and also limited by our abilities to draw. Usually, we're only going to use design spaces for 1 and 2D problems. But just know that this notion or this concept also extends to 3 and 4th dimensions. If somehow we could brain blast it and we can perceive higher dimensions, this can work for us. Okay. I make it sound really fancy, but it's nothing more than just a quick one. So a design space can really be helpful in visualizing kind of the permissible values of our variables. Okay? So in one dimension, our design space is nothing more than just a number line. Okay. So a number line for our design variable x, okay? And so let's say that we have two inequality constraints. So let's say that x has to be greater than or equal to some value a, and x has to be less than or equal to some value b. Okay. If we mark on the number line the values of a, and of course, a has to be greater than or equal to a has to be less than or equal to b. This makes no sense. So let's say the value a is right there on the number line. Value b is right here. And so if our value x has to be greater than a and less than b, that means our permissible region exists in the space in between. And so we say this is the permissible region or the valid region. Sometimes I'll say valid. So our optimal value of x, we're constraining to be somewhere in that range. But most commonly, so in one dimension, it's a little trivial just because, it's easy for us to visualize, an upper bound and a lower bound, without really any pictures. Okay. But in 2D, it really becomes valuable. So in 2D, remember we have two design variables. We'll call them x1 and x2. Just to keep things simple. And if we treat these values of x1 and x2 as kind of the Cartesian coordinates, we can plot our design space in kind of two-dimensional space. Our coordinate axes here, we'll say the horizontal axis is x1. So x1, the horizontal axis represents possible values for x1. And the vertical axis will represent possible values for x2. Okay. Right. So a location on this plot represents a paired value of x1 and x2. Okay, so that's a single, we call that a single design. And then since those the values of since we'll have a value for x1 and x2, we can kind of visually or physically kind of plot it within this space. Right? Let's say that we have a point right here, we'll call it P1. So P1 right there can represent a single value or a single design or design point for this optimization problem. Right, and just like the one-dimensional case here, we can use this design space to represent our constraints. Right. So let's just stick to kind of simple inequality constraints as well. So we'll say that x1 is bound by two values. So that x1 has to be greater than or equal to 1, and x1 has to be less than or equal to p1. Yes. And so if we plot the values for a1 and b1, so we'll say this is a1, right here is b1. These are constraints on x1, so we're going to put it on the x1 axis. And so we can extend those lines upwards, okay? And so those dotted lines kind of show us kind of our permissible region or our valid region for x1. Okay? But we also have permissible values for x2 as well. So let's say that x2 has to be greater than or equal to a2, and x2 has to be less than or equal to b2. So we'll plot these on the vertical axis, so we'll have A2, 2. Again, we kind of draw lines. Show that. And so now we have a rectangular region. Okay, so this rectangular region shows us the valid region for this problem. So any design point that falls within that valid region is a valid design point. Okay, if we have a design point that falls outside this region, so let's say that we have one, you know, maybe we'll have one that I'll use here. Let's say that we have a design point P2 that's on the left right there. Okay. So P2, even though P2 satisfies the constraints for X2, so it's between the upper bound and the lower bound for X2. You can see that it's outside of the valid region for X1. So P2 here is an invalid point. Any questions on design spaces? It's a nice tool, and it's one that is going to be really useful for us once we start to get to the active function. Okay. I know right now it kind of seems a little silly because we're working with kind of very simple constraints, but constraints can actually become pretty complicated as well, right? So here we have kind of a simple rectangle, but it's also possible to have kind of multiple variables in a constraint. So maybe our constraint region, maybe is something like this, right? And so in more complicated cases, being able to visualize the constraint or the valid region is something that's really valuable. All right. So then let's get to the final topic for today, which is the idea of an objective function. So objective function, just to remind you, was our function f, and it was a function of the design variable. Okay. So up to this point, we've covered the concept of a design variable. The design variable is nothing more than just the parameters of our system that we can tweak throughout the design process. We've covered the concept of a design constraint. A design constraint is just a limitation or a constraint on the values of the design variables that that tell us which values are valid or which are not. Okay. We haven't really gotten to the crux of engineering of optimization, right? Because the whole point of optimization is for us to determine, the best value of these parameters, or in other words, for us to determine which designs are better than the others. Okay? And so the objective function is the mathematical tool that allows us to do that. So the objective function is a mathematical function. It's a mathematical function that allows us to compare the performance or the result of certain designs compared to another. Because it's one thing for a design to be valid, right? It's another thing for a design to outperform one or the other, right? And that's ultimately what we strive to achieve in optimization. It's the one that's going to get the best performance given our particular design. Okay. So The objective function, takes some mathematical form, but the form that it takes, depends on the goals of your design, right? Because every engineering project has different design goals in mind. Okay? All right, so let's look at some examples of some common kind of engineering goals, for design and how we kind of formulate that into an objective function. Okay. In fact, we've already kind of seen one, from on the previous example. So one very common goal in engineering design engineering design is to minimize the cost. Okay. That is like almost always a design goal, a design constraint. Okay. Engineering would be a lot more fun if your manager told you just spend however much you want. The budget is infinite. But the real world usually doesn't work like this. So we've already seen this, and so if we're looking at the cost of constructing a structural column, it would be the volume of the column times the times the price per cubic foot per cubic inch of the material. So that was the equation that we found earlier. So this is what we call the material. Of course, that's not the only cost that's associated. You also have to pay for the labor that's involved in installing the there may be some permits that you have to buy or stuff like that too. So cost is always one. The cost is usually a pretty straightforward thing. Usually you can account for the cost kind of, even before you construct it, right? Usually it's a straightforward equation of, how much material you're using, how long it's going to take, how much labor it's going to take to produce it, okay? Another very common performance metric would be some kind of, or objective function, excuse me, some kind of performance metric, of the design at the end. So if you think of the design of like a car, right? So some performance metrics of the car might be its top speed, it might be its acceleration, how quickly it kind of gets off the stop, how quickly it brakes. I'm strictly just thinking of things you can quantify. The gas mileage, things like that. All of these can get factored into the objective function in some way, because if those are important goals for your design. So say you work for Ferrari or something like that, and you want to maximize these things. These are important metrics for you to know. Okay. Right. So performance metrics, of course, these are things that you want to maximize. Another thing that you would often want to minimize is any kind of inefficiencies in the design, and so any kind of power inefficiencies, friction, things like that. You want to minimize the inefficiencies or maximize the efficiencies. Okay? And there's dozens more, right? So there's a lot more metrics. Maybe you want to maximize power output, things like that. Okay. So, the objective function, I think, is really kind of the encapsulation or the representation of what you hope to achieve with your engineering design. So stating your goals or stating what you want to be factored into your objective function, that's usually the easy part, right? So you're coming up to you're starting engineering design. You want to say you want to maximize performance, you want to minimize costs, you want to maximize efficiencies, things like that. Okay. So coming up with the idea of what your objective function should have is easy. The hard part of objective functions is actually putting it in a mathematical form that you can actually work with. Because oftentimes, especially, for the early parts of the class, that mathematical form has to incorporate your design variables in some way. Because remember, the function that our formal definition said that our objective function has to be a function of our design. And that can be pretty tough, especially when you have a complicated system, right? So, just to give you an example, right? So let's say that you want to, you're working for Ferrari, right? You want to maximize the top speed of your car that you're designing, right? And one of the design variables that you're considering is the diameter of the tires, right? So you want to form an objective function that takes the diameter of the tires and define the relationship with top speed. So what that means is that your objective function needs to incorporate top speed to some degree. Of xi, some metric for top speed. But in order to actually get it into a mathematical form, you need to know the relationship between top speed and the tire diameter. And that's not quite easy to do, right? And so if you were to take any car, right, and try to find out what its top speed is as a function of the tire diameter, because if you increase the tire diameter, yeah, it increases traction with the road, but it also increases friction as well. It's going to increase the amount, the load on the engine as well. So that relationship is often going to be pretty difficult to get. And oftentimes you actually have to rely on some kind of computational simulation, like finite element simulation to get, right? So for the purposes of this class, for the most part, we're going to be focusing this class more on the algorithms, how to find the optimal values. So just for this class, I'm gonna be giving you the objective function for the most part. But just know that, the act of finding an appropriate objective function for a given engineering system is challenging, and it's something that's not trivial at all. We'll get into it more kind of near the end of the class. You're definitely going to be doing it for your final project, but there's a lot of steps that we need to take to get. Okay. So for the purposes of this class, you can assume that the objective function will be given to you. The design variables will be given to you. It's just that, your goal is to find the best values of the design variables for that particular objective. Okay. All right. Any final questions before we wrap it up for today? Okay. All right. So that's all we got time for today. So when we come back on Tuesday, I have some examples for you. So we'll actually get to design that column that we've that I kind of used all over today. So I'll actually put some numbers on it. We'll visualize it and we'll see how it works. All right, so thank you guys for coming today. Hope you guys had a good first week. Hope you guys had a good rest of your day, and we'll see you guys on Tuesday.
Okay.
What?
You said you're working 11 hours.
Thank you.
Yeah.
Are you gonna work weekends, huh?
It's gonna be pretty tough.
I don't know. May I take your stuff to the lake?
No, I'm done for the day.
So the official list. Not gonna accept the game. But I think I should be able to make it. It's fine. I'm gonna try to do it. But just I will.
I'm so hungry.
Yeah.
Anything.
No, I'm staying here. Hey, Professor.
What's up?